This is problem number 2 on the sample test problems for test number 2. The function on the left, f, gives the height in inches, h, of a particular plant as a function of number of months, t, it has been growing. Before we move on, I'm just going to start labeling these things with their letters. So in this case, the function is f, and so the vertical axis here is h, height in inches, and the horizontal axis is t, which is time, and it's measured in months. And continuing on, the function on the right, g, gives the number of gallons of water per week, w, which the plant needs as a function of its height in inches, h. That is h equals f of t and w equals g of h. Okay, with the graphs labeled, let's move on to the first part of this long question. A, find f of 4 and explain its meaning in the context of this problem. F of 4, f is this graph on the left, 4 is the input, so we go right here to 4, we go up to the curve, we go to the left, and that looks like maybe 11.5. So that's our answer to this one. F of 4 is around 11.5. A lot of folks forget to write that when I ask test questions like this. Find f of 4 means numerically write that sentence and then explain the meaning. Some people just write the explanation, but they don't write down the f of 4 is about 11.5. Okay, and so the explanation in this problem, well, let's see, 4 was the input here. That was time in months. So a 4-month-old, is this a tree? Plant, 4-month-old plant. And then somehow that's related to 11.5, which was the output, which is the inches that the plant has grown to. So I guess the sentence is something like a 4-month-old plant has grown to 11.5 inches, or is 11.5 inches tall. Part B, find g of 14 and explain its meaning in the context of this problem. So g of 14, 14 is the input, it's right over here. We go up to the curve. We go to the left. It looks like it's something a little bit under 2.5, maybe 2.4. And let's explain the meaning of this one. So 14 is the input, that's the height in inches. So we have a plant that's 14 inches tall, and 2.4, that was the output. And we can see there on the top right, the output is the number of gallons of water per week that the plant needs. So I think our sentence is something like a 14-inch tall plant needs 2.4 gallons of water per week. Part C, find g of f of 3 and explain its meaning in the context of this problem. Let's try this one. G of f of 3. So we start from the inside and work our way out when we have composition of functions. So we begin with f of 3. So that's the left-hand curve, that's f. So we go to the input, which is 3, up to the curve, over, and that looks like maybe about 7.5. So what we've just established is that f of 3 looks like it's around 7.5. So then what I'm interested in finding here, this was g of f of 3, that's the original question. We've just now made some progress. That's really asking us to find g of 7.5, the number we just found. So g of 7.5, well, that's the right-hand curve. So we'll go to 7.5 as the input. I think that's this one. And we go up to the curve, and then we go to the left, and it looks like that might be about 0.75. So I think this is around 0.75. And we want its meaning in the context of this problem. Okay, so I'm going to use 3 numbers as I explain this, but I'm only going to write 2 of them in the sentence that we actually write in the answer. So the original input was 3 somethings. Somehow that 3 turned into a 7.5, and then the 7.5 finally turned into a 0.75. So there were 3 numbers here. So the first one is the 3. That's the input for the f function, which is measuring time in months. So we have a 3-month-old plant. That went to the number 7.5 in green. And 7.5 was the height. So a 3-month-old plant is 7.5 inches tall. That's the left-hand graph. And then we come to the right-hand graph. A plant that's 7.5 inches tall requires 0.75 gallons of water per week. So when we write the sentence, actually, we're not going to use all 3 of those highlighted numbers. We're going to use the input and the output. So the only ones that I want to use are the original input and the final output. 7.5 that's highlighted in green, that's an intermediate number. And to be honest, it does not belong in the sentence that we write here. So the 3 that we started with was the age in months, a 3-month-old plant. And I'll say something that I won't write. 3-month-old plant is 7.5 inches tall, and a 7.5 inch tall plant requires 0.75 gallons of water per week. Okay, next, part D. What is the average rate of change of the height of the plant from month 2 to month 5? Be sure to give appropriate units. Okay, so let's try this one. So average rate of change, and we want the height of the plant between months 2 and 5. So which graph is that? That must be the left-hand graph. So month 2 is here, month 5 is here. And what we need to do is just use our basic average rate of change formula. Essentially, it's just the slope of a secant line. It's a change in y over change in x. So what we need to do is find 2 y values, or 2 h values in this case, that go with our inputs of 2 months and 5 months. Okay, so this number over here is close enough to 4. I'll just call it 4. The next number looks pretty darn close to 15, so we'll say it's that. So basically our inputs are 2 and 5, and our outputs are 4 and 15. So then we'll write down here our average rate of change. So rate of change average, it's normally change in y over change in x. In our case, it's different letters. It's change in h over change in t. So we need the 2 h values. Those are in blue up here on the left, 15 and 4. Doesn't matter which one goes first. I'll put the big one first. Divide by change in t. We need the 2 blue t values. It's this 2 and this 5. Here it does matter what order we put them in. We need to put them in the same order we put the dependent variables on. So the 15 goes with the 5. So we better put the 5 first because we put the 15 first upstairs. Didn't have to do that on top. We could have done on top 4 minus 15. Then on the bottom, it would have to change as well, 2 minus 5. So either way, we should end up with this positive 11/3. And we said to write the appropriate units. So all we need to do is write down the units for h over the units for t. So the units for h are inches, and the units for t are months. So this plant grew 11 inches in 3 months. Said another way, on average, it grew 11/3 of an inch per month. That's assuming it grew at the same linear rate the whole time. Part E, at what average rate was the number of gallons of water required each week changing when the plant grew from 5 inches to 15 inches? Okay, so the number of gallons of water, that's the right-hand graph, and we're going between 5 and 15 inches. So this is exactly the same problem just over here on the right. So we go to 5, which I think is this. I want to do this one in blue because it's another rate of change one, so let's stay blue. So we go 5 here, and I think the other number was at 15. 5 inches to 15 inches. Okay, so 15 inches is out here. And again, we need the y values, so we're going to go up to the curve and then to the left. And it looks like that's at 2.75. And then from 5, we'll go up to the curve, go to the left, and we'll just say that's about 0.25. Maybe it's a little bigger. And it's another average rate of change formula, so it's another slope of a secant line. It's a change in y over change in x with those 4 blue numbers. So let's bring those numbers down here once we write down our formula. So rate of change average, again, standard letters for us are change in y over change in x. In this case, though, the letters are W and H. So now we just need to grab the numbers from the graph. So the W numbers on the vertical, 2.75 and 0.25. I'm looking at the numbers in blue. So we subtract, either order is fine. And then the change in H, that's on the horizontal axis. And now we got to subtract in the same order. So because we did 2.75 minus, we better do 15 minus on the bottom. So it's going to be 15 minus 5. So let's clean this up. Upstairs we get 2.5. Downstairs 10. Simplify that to 0.25. And again, I think we're supposed to, I didn't write in include units, but pause the video here if you haven't written the units down and think about what the units are. So in this case, the units are W units over H units. So the W units are gallons of water per week over the H units, which are inches. So we didn't need a sentence, but we could come up with some explanation for what this means. I'll go back to this fraction first. Over the course of 10 inches of growth, the plant needs an additional 2.5 gallons of water per week. Or if its water needs were a linear function of its height, then we could say that the plant, for every inch that it grows, the plant needs another 0.25 gallons of water per week. Okay, part F. Approximate the instantaneous rate of change of G when H equals 4. Be sure to give appropriate units. Okay, so finally now we're going to do some calculus. Instantaneous rate of change. For us, that's synonymous with slope of a tangent line. So we want the tangent line of the G curve at H equals 4. So we come up here. We're going to go to H equals 4. Let's go purple. So H equals 4 is there. We'll go up to the curve, which is there. And what I'm interested in is a tangent line at that point on this curve. So you're going to get your best straight edge and draw your best tangent line. You're going to make sure that it hits the graph. So let's make sure it hits the graph. Just pause there because I got questioned by security. It was 5:30 on a Friday night. This is not a proud moment for me. Okay, so we've got our tangent line. That's good enough. And what we're interested in is the slope of that line. So the instantaneous rate of change, let me write that slightly differently. Okay, rate of change instantaneous is the slope of the tangent line. And so what I'd like us to do, some folks are in the habit of trying to pick 2 points that are really close to each other, for example, that one, and then maybe try to find the change in y over the change in x. And it's just not good because the points are so close to each other that the change in y is really small and the change in x is really small, and you're estimating all these really small numbers. And when you divide and there's something small on the bottom, it tends to make the fraction big. So any kind of error you make upstairs gets compounded. So how about instead of picking points near each other, which was kind of the idea with the tangent line, we'll pick points that are far away from each other. So for example, I'll pick this point right here. It looks like it's kind of right on the grid. That one looks like it's about 17. And then if I go all the way out here, maybe 2.25. So there's one point that's on my tangent line, any point on the tangent line. And then let's pick another nice point on the tangent line. Let's go ahead and pick the original point, actually, the one at 4. So this point has h equal to 4, and then the w value, well, it's close enough to that quarter that we had from before. So let's go ahead and use, I'll make this guy green now. So we're going to use these green numbers here 4 and 17 are the h values, and then 2.25 and 0.25 are the w values. So let's do our slope calculation down below. Hopefully we can remember all these numbers. Slope of the tangent line equals, okay, downstairs was 17 minus 4, upstairs was 2.25 minus 0.25. I'll go up there to show you, but really I just want to confirm that I got it right. Okay, I think that's good. Change in y over change in x. And so we calculate, upstairs is a 2, downstairs is a 13, and that's our answer. It says include appropriate units. So remember, the units for the derivative are always the, I'll write this over here. So the y prime units are always the y units over the x units. In our case, we don't have x and y. We have w and h, so that's where those numbers go. So let's bring that back to our unit description. So the W units are gallons per week. And the H units are inches. So in this case, we could say something like at H equals 4, that is, if we have a plant that's 4 inches tall, then the rate at which it needs water is increasing at 2/13 of a gallon per week per inch. Only at that height, at 4 inches, the rate at which the plant needs more water as it grows, it's about 2/13 of a gallon per week per inch. Now there's a lot of latitude for this question in terms of getting full credit for an answer. I can almost guarantee that this answer is not the one that I wrote in the answer key, and that's okay. Just has to be something nearby. And the way you show me that you know what you're doing is by drawing up here a tangent line. It's in purple at h equals 4. All right, let's come back down here to G. It says find f prime of 2 and explain its meaning in the context of the problem. So this is another slope of a tangent line. So let's go up there, f prime of 2. So f is the left-hand graph, f prime of 2. So here's 2. It's a point we were already interested in before. We go up to that point there, and then we draw our best tangent line. So again, we'll draw our tangent line in purple. And then we'll pretend that didn't happen. That looks okay. All right, so we just need 2 points on this tangent line. We'll go ahead and use this one that's in green already. It's got a 2 and it's got a 4. And then any other point that's on this line, again, I encourage you to pick a point that's very far away. So for example, maybe we could pick this point up here that already kind of happens to be in blue. That's a 5, and over here is a 15. So let's grab those numbers. Change in y over change in x. 15 minus 4, 5 minus 2. I need to double check. Okay, I think that's right. So we get 11 over 3. And in order to explain the meaning in the context of the problem, I always like to think of units first. So again, it's the dependent variable units over the independent variable units. In this case, we didn't have y and x, we had h and t. So h units over t units, inches per month. Okay, so what's the sentence? I guess that means that the plant at that moment in time when the plant is 2 months old, the plant is growing at a rate of 11/3 inches per month. You could also say the height is increasing at 11/3 inches per month. So let's write a sentence, something like that. A 2-month-old plant is growing at about 11/3 inches per month. And if we looked at a 3-month-old plant, it could be a completely different growth rate. We're just looking at that plant that is exactly 2 months old. It's on its 2-month birthday. And at that moment in time, the growth rate appeared to be about 11/3 inches per month. Part H, by how many gallons per week per month are the water needs of the plant changing when the plant is 2 months old? Describe in detail how you found your answer. Okay, this one seems like it's a doozy. How many gallons per week per month so are the water needs changing when the plant is 2 months old? Okay, so the 2 months old, let's start there. That 2 months is an input. Is it an input for F or G? So we think about this. Let's see, that's time, and F was the one that took a time number into it. So we've got a plant that's 2 months old, and somehow we're trying to relate that to the water usage. We want to get down to, gallons per week here, and the function that has to do with that is G. And what G does is it needs a height in order to be input into it and spit out the number of gallons per week. So I think what we're really looking at is something like this. I haven't done a derivative yet, and we'll have to do that, but I think that we've got a 2-month-old plant. We can throw that into the F function to tell how tall the plant is, and then we can throw that number, the height, into the G function to find out how much water it needs. Okay, so we've got the basic idea here, but what we need to do is find not just G of F of 2, but actually we need to find the derivative of this function. So what I'm interested in is the derivative of this, so d dx of that thing. Actually, maybe x is not the best choice because we don't have x in this problem. We have t. So we want the derivative of that function with respect to t. And then we want to evaluate that thing after we've done the derivative at t equals 2. So I'll just write that down at the bottom there. So let's see if we can't figure out how to do that. So the first thing we need to do is find the derivative of g of f of t. Don't plug in 2 yet. We need to do this derivative for a general t. And I'm hoping we see this is a composition of functions. We have an outer function and we have an inner function. And when we have that, we have a chain rule. So we need to know the chain rule version, the formula version of the chain rule in order to write down the formula here. So here's the formula. It's the derivative of the outside function evaluated at the inside function. Notice it's just f of t, not f prime of t. That's the outer, times the derivative of the inner. Derivative of f is f prime. So that right there is what we're trying to calculate. And once we do that, we're going to plug in t equals 2 at the end. I just put a little vertical line there. That's a common way to say plug in some number after you've finished. So now that we've got our formula, I'm ready to make all of those t's 2's. Okay, so we need to find g prime of f of 2 times f prime of 2. All right, let's go a little bit further here. I'm just going to copy this f prime of 2 for a moment and figure out what's really in these parentheses. So the question is, how much is f of 2? And whatever we get, we're just going to throw that into here. So f of 2, let's go back up to our f function. I think that's way up here at the top. So f of 2, that's this left-hand graph. So we'll do this in our erasing thing because it's getting cluttered. So f of 2, we just go over here, it's 4. We've seen that before. So really f of 2 is 4. And this turquoise highlighted thing is just 4. So really what I want to know is what's g prime of 4, what's f prime of 2, and whatever I get, we multiply them together. Now normally, finding g prime of 4 would be kind of a pain because you'd have to draw a tangent line in and then pick some points on it to estimate its slope. And then you'd have to play the same game to find f prime of 2. But I'm so clever, and actually I shouldn't take credit because I got this from one of my predecessors. He's so clever that I think he built in the answers to these 2 little pieces in the previous questions. So I think we just have to grab them. G prime of 4, that's the derivative of the water rate of change, instantaneous rate of change when h is 4. Aha, it's just the answer to this question, 2/13. So this is 2 over 13. We'll circle it in blue. It goes right there. That's g prime of 4 times f prime of 2. Okay, f prime of 2 is actually just what we found in the previous question. There it is, f prime of 2. So f prime of 2 we found was this 11/3. We throw it over here. Multiply our fractions across, 22/39. And then I guess that's it. We can put units in if we're so inclined. Remember the units here. Well, I guess the units actually are part of the question. It wanted to know how many gallons per week per month. And I think that's what we've got here. Gallons per week per month are the units of this final thing. So we'll write it, didn't have to, gallons per week per month. Input a plant that's 2 months old, and its water needs are changing at 22/39 of a gallon per week per month. That is to say, every month that passes, the plant gets taller, so it needs more water. How much more water does it need? It needs 22/39 of a gallon per week, an additional 22/39 of a gallon. So, you know, like 2/3 of a gallon per week, more than it did before for every month that it grows. But again, that's only at this particular moment in time, t equals 2. At t equals 2.1, this fraction that we've got highlighted in yellow will probably change. And I can also say that fraction in yellow, there's no chance that's the same as the answer in the answer key. I haven't looked at it yet, but you know, all of this is approximations, so there's a lot of latitude in terms of getting full credit on a problem like this. Okay, let's finish up. Part I. For what values of t is f double prime negative? This question is a breath of fresh air compared to the previous one. F double prime, hopefully you make the instant connection that that has to do with concavity, and negative means concave down. So this question is really saying, when is F concave down? So we come up here to the F graph on the left. So I'll highlight some stuff here in, well, we'll just highlight temporarily. We've got part of the graph from here to maybe around there. That graph is concave up. And then here at the end, it's definitely concave down. So someplace there in the middle is where it changes. And we're looking for the places where this graph is concave down. So you can kind of pick anywhere, somewhere in the middle of this sort of straight line part. I'll go ahead and say that it happens at, I don't know, maybe at 3. So maybe I'll say that's the point where it changes. It was concave up over here and concave down the rest of the way. So we'll say that it's concave down from 3 and then onwards. So for what values? For any values of t bigger than 3. Again, that's an approximate. If you had said 4, no problem. If you say 6, that's a problem. If you say 1, that's a problem. But really anything near the middle of that graph where the concavity changes. Finally, part J. What are the units of g double prime of h? Okay, so let's start playing the units game here. I don't know what's going on with g double prime, but I feel pretty good about g prime units. I know that the units of g prime are the output units over the input units. So I'll write it that way. Sometimes we write it as a change in y over change in x. I'll put output over input. And the output for the g function was gallons per week. And the input for the g function, that was the h variable, that was the height, that's inches. So the units for g prime are gallons per week per inch. And then we'll finish up here by then thinking about the units for g double prime. Okay, it's the same kind of idea. It's an output unit over an input unit. Okay, the output for g double prime, well, let's see. The output, I guess, okay, so I paused there because I didn't quite have a good way to say it based on what I'd written there. So maybe I'll undo that last writing. So we'll come back to here. Okay, g double prime units. So what we want here are is to think of g double prime as being the first derivative of the first derivative. So we know that the units of any derivative, that's what we've got written up there in black. If you have a derivative, you just have to do the output over the input. So we do have a derivative. G double prime is a derivative of G prime. So I want the units of G prime. That's the original function. I'm thinking of that as the original function, divided by the units for the input. And the units for the input are still H. So the units for G prime, we just calculated that up there in black. It's gallons per week per inch. All of that is the G prime number divided by units for H. Well, that's also inches. So it gets pretty foggy up here, but the units for the second derivative of G are gallons per week per inch per inch. And I guess if you wanted to, you could mush those together. That's what they do for acceleration, right? Gallons per week per inches squared. But square inches have to do with area, and nothing in this problem has to do with area. So don't feel like you need to do that. I do think it hides sort of what's going on. Whew, that was tough.